These are particles of radioactive fallout. And this is how a single particle looks magnified several hundred times. A radioactive piece of matter from a nuclear explosion. These few particles can't do us any significant harm. But should there be a nuclear attack, many billions of them would fall from the sky and settle to Earth, releasing radiation that could cause sickness or death in the area where they fall. To begin with, it may be surprising to know that radiation is something we live with every day. Far back in time, back before there was an Earth, there were flaming fireballs in space. We call them stars. And there are millions upon millions of them. Each star, like our own sun, is a raging nuclear furnace that shoots out showers of particles too tiny to be matter as we conceive it, along with invisible forces that we call radiation. This radiation and these particles travel through space at fantastic speeds until they strike some other matter which may make new flares of radioactivity. They strike wandering asteroids, moons, and planets such as our own. Everything in space, Earth included, receives this radiation.
Skies partly cloudy this afternoon, clearing but...
Background radiation is all around us in tiny quantities. Nature even planted unstable atoms deep inside the Earth itself. They decay one by one, here and there, in a barrage of inconceivably small and silent explosions. Each explosion is another spark of radiation. All life on Earth has reached its present form in company with radiation from this naturally occurring radioactivity. Extremely thin, with extremely low-level intensity, it has always been with us. It is nothing new. We don't worry about the small amounts of natural background radiation. But to safely handle larger amounts, we must keep our distance and shield ourselves. For as the amounts increase, so do the dangers. The amount of energy generated by a nuclear explosion is enormous. Near the crater area, there is almost total destruction from blast and heat. And now, large amounts of pulverized debris and molten earth are pulled up into the mushroom cloud. This is where radioactive fallout is formed. The radioactive atoms produced in the explosion join with the particles of earth and debris. The mushroom-shaped cloud forms and climbs higher. It now contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. The larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer they remain aloft, the less dangerous they are. But the heavier particles, spread by high-altitude winds, fall to the ground within 24 hours. Several miles from the explosion, they are about the size of table salt or fine sand. These are the most dangerous, because they carry the greatest number of radioactive atoms and so emit the largest amount of nuclear radiation. Which brings us to an all-important fact. Deadly as radiation can be. And this gives us an invaluable ally: time. Suppose a nuclear explosion takes place at 12 noon. By 1 o'clock, the total force of the residual radiation is at a high level. By 7 o'clock, it's down to 1/10. In 2 days, although still dangerous, it's only 1/100th. But in 2 weeks, it's only 1/1,000th. With this decay rate in mind, consider radioactive fallout conditions which might confront us after a massive attack. Within an hour, fallout would be a serious problem in the vicinity of explosions which occur on or near the ground. By 7 hours after the attack, the fallout area covers more and more of the country as the prevailing winds expand the fallout in a downwind pattern. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people can even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than time. Fortunately, we have another ally: distance.